Okay, we are going to start on current electricity. The first topic we are going to do is what is current. These are our lesson objectives. Electricity is an essential part of modern society as it supplies energy to power our electrical appliances such as light, heater, computers, and handphones. Current electricity topic is to understand the basics of properties and quantities of electricity. And there are three important quantities to know or understand. They are current, voltage, and resistance. We start with current of electricity as it can be easily visualized and understood. What is current in electricity? We use a simple simulation of a simple electric circuit that comprises of a battery, a lamp, a switch, and some connecting wires. Though we cannot see electricity in the circuit, we can see the effects of electricity. When we close the switch and complete the circuit, and the lamp lights up due to a flow of electricity, some of you may be thinking, why does the switch need to be closed in order for the lamp to light up? Isn't the lamp already connected to the battery before the switch is closed? Don't all our electrical devices only have one wire connected to it? So pause and think about it for a while. It's because electricity needs to flow from the battery to the light bulb, and then from the light bulb back to the battery. Without closing the switch, there is no complete path for the electricity to flow, and that flow is the current of electricity. So why is there only one wire connected to our electrical device? And how does the current actually flow back? It's because that one wire is actually two or more wires encased in that wire. Something like this. So this is one wire that you see outside, but actually there are two wires in there. And your plug actually consists of at least two pins which is connected to a wire. So one wire for one pin. Okay, so actually there are two wires inside. And of course this will be connected to your electrical device. So one flow in, one flow out. So what is current and what is actually happening in the circuit? The current of electricity is actually a flow of electrons in the circuit. And using a simulation, we try to visualize what is happening in the electrical circuit. So this is the electrical circuit that we just seen. Okay, what is actually happening is that there's actually a flow of electrons within the circuit. The balls in the wire are actually free electrons in the wire. When we close the switch, which completes the circuit, the battery is now able to pull the chain of electron balls towards the positive terminal of the battery, and at the same time it also pushes the chain away from the negative terminal of the battery. Together, like a queue of people, the free electrons along the complete chain would be able to move together. But however, if the switch is open, the complete chain is right now broken, and the electrons in the path actually stops moving and the flow would naturally stop. Using another circuit, we can see the effect of open and closed switch. The one with the complete path would still allow electrons to flow through even though there's a switch that's open. So that's actually what's happening. So there's a complete path and the electrons will be able to flow in this complete path. But this path is broken, so the electrons is not able to flow, even though here is connected to the battery. But of course, when you switch this on, again, complete path, both will be able to flow. And likewise, if we switch this off or break the cycle, you find that only this path would be able to flow. However, of course, if you break the entire flow over here, both would not be able to switch on. What are the effects of a larger and smaller current for our simple circuit? We can adjust the current through by changing the battery. if we use a stronger battery, or a battery with a higher voltage or EMF, the current flowing through in the circuit will be larger. So using a simulation, we explain what do you mean by a larger current. A battery strength is defined by the voltage of the battery. So you find that a stronger battery will have a higher voltage. So let's just close the switch again and you see the light. Let's see what will the effect be if we increase the voltage. So as you can realize, the light bulb become brighter. But what is actually happening inside? Okay, let's again go back to 9 volts. Okay, and we show the electrons. So what happens when we increase the voltage is that the current becomes stronger. So note from the simulation, as the battery increases in strength, the movement or the flow of the electrons in the wire is actually faster. So it is because the stronger battery is able to pull and push with a larger force, and the chain of electrons movement will be faster. Thus, essentially a faster flow of electron charges means a higher current in the circuit. And how does it lead to the light bulb glowing brighter? Think about your hand gripping a long length of moving rope. How does your fan feel differently if the rope is moving slowly or compared to the rope is moving very fast? Similar to a hand holding a moving rope, a faster moving rope will rub more with the hand and the hand will feel hotter compared to a slower moving rope. In this case, the faster movement of electrons when moved past the filament lamp will rub and hit against the atom of the filament lamp. This excites the atom of filament lamp, which makes them hotter or rise in temperature. And overall, this results in the filament lamp glowing brighter. So generally, a higher current flowing in a lamp results in brighter light bulbs. Of course, we cannot use the brightness of a lamp to accurately determine the value of a current. Current is measured using a device called ammeter, and the circuit symbols looks like this. And the SI unit for current is ampere. The formula for current is I equals to Q over T, where I is current in ampere, Q is the charge in coulombs, and T is the time in seconds. So current is actually the measure of the flow of electric charges, and simply it is the amount of electrical charges flow per second. As each electron has the same charge, it is as good as counting the number of electrons flowing per second. So the idea is that a larger number of electrons flowing through per second lead to higher charges flowing through per second, which means that a higher current value. Let's just do some simple calculation. When a lamp is turned on for 1 minute, the total amount of charges flowing through was 15 C coulombs. What is the current in the lamp? So we just apply a formula, current equals charge divided by time. So it's 15 C divided by 60 seconds, because again, time in this case is in seconds. So 0.25 ampere. If a lamp was switched on for 10 seconds, okay, and the current is flowing through is 1.2. Okay, when you calculate the total number of electrons passing through a lamp during this 10-second interval, and given that one electron has a charge of 1.6 times 10 to the power negative 19, so what you need to do is to apply the opposite, rearrange the formula to charge equals to current times time, and charge is equals to 1.2 times 10 seconds, so 12C. Okay, and since we know that one electron has a magnitude of 1.6 times 10 to the power negative 19C, so 1C essentially has 6.25 times 10 to the power 18 electrons. And 12C, of course, just multiply by 12, you have this number of electrons. Okay, that's all for now for this lesson. Please subscribe and support my channel. For my other physics video lesson arranged according to topics, please visit my blog at boringphysicsteacherswordpress.com. You can subscribe to my channel to be informed when I upload new physics video lessons. Thank you.